Welcome to Lecture 2. So we are going to start the introduction to multi-agent system. In this class, I'm going to give you a few examples of scenarios where multi-agent system can be useful and which demonstrates the central issues in the design of multi-agent systems. As we have discussed in the last lecture, the main challenge to a multi-agent system lies in the autonomy of the agents, is decentralization of the system and the lack of global knowledge. A protocol specifies how an agent should act in the environment while interacting with other autonomous agents. So our challenge is therefore to design protocols that enable the agents to function in a reasonably well manner and be able to coordinate with each other. Right. So in this lecture, we will discuss in particular two scenarios that face such issues. First of all, I'm going to talk about multi-agent pathfinding. This scenario refers to a situation where you have mobile robots traversing in an enclosed space while trying not to bump into each other. You can watch this video on the slide for more information about the type of industry application that I'm talking about. But here you can imagine we have a warehouse with a number of bots who really have limited capabilities. Then what they do with them, for each bot, there is a starting location and there is a goal location, and the bot would like to go from the starting location to the goal location. And suppose every agent have a map of the space, so it's quite easy to find the path from any location to any location, but because the existence of other agents in the space, one crucial thing that need to be taken care of is that they do not collide with each other. One possible mechanism to ensure that is to implement some type of centralized control to all the agents in the space that not only finds the optimal path from one location to another for the agents to follow, but also whenever there's a chance for agents to meet, we as a central controller will maneuver them in a certain way that they do not bump into each other. But if you think about a situation when you have hundreds of agents working in a relatively large warehouse, then if you implement a central control system, the amount of computation that need to be taken is quite high. So really, if you think about this type of industry application, we would like to see each bot as an individual who is able to function in an autonomous way, and therefore we would need a solution that somehow release the sort of power of decision making to the agents themselves. So we want to implement certain autonomy into each agent while ensuring that they have sufficient coordination with each other. Right? And this requires the implementation of certain constraints, which we call social laws. In this course, I will be constantly referring to some formal mathematical definitions. And therefore it is very important that we get used to such mathematical language. So formally speaking, the multi-agent pathfinding problem can be defined as a tuple. And in this tuple, there are several components. The first will be a set of agents. And here we assume that there are m number of such bots traversing in the space, and I call them A1, A2 up to AM. And then I have a number of positions in the physical space, but abstractly I'll view them as a set of nodes, and I denote it by V. And also there are links between the nodes. These are just pathways from one node to another, and that set of undirected edges is denoted by E. And then we have a function S, which assigns every agent a starting position, and also a function G, which assigns every agent a goal position. So once we designed this problem, then we want to solve the problem by finding a solution. A solution in particular for a particular agent, it will be just a path that links the starting location of the agent to the goal location. Right? So a path formally would be a sequence of nodes, v0, v1, v2, up to vk. So the path is having a length k. So it contains k edges, and where v0 is a starting location, which is S of ai, and vk is the target location, which is g of ai for every I. Right? So suppose we have two solutions, one for agent I and one for agent j in the space. We say that pi and pj will collide if for some s that's within their range, so s is between 1 and the minimum of k and l, vs is equal to us. So this means that at this particular instance in time, where we have the agent I colliding with agent j at the same location, namely vs. Right. The solution for the multi-agent pathfinding problem consists of a solution to every agent such that we do not find any pair of agents who ever collide during the course of their traversal. So of course, if you think about just the scenario where the set of agent A contains a single agent, so suppose there's no other agent in the space, the easiest solution will be to compute a shortest path from the starting location of the agent to the target location. However, when you have multiple agents in the space, and this means that potentially if everyone just simply followed their shortest path, it will likely be that they would collide at some point. And therefore, we need to relax the condition that they are following their absolute best solutions, but they need to somehow coordinate with each other. So we need a solution that is somehow good in terms of certain performance measures, but one thing that we want to ensure is that they do not collide with each other. So that is the problem in a mathematical way. We want to break down the question into a number of sub-questions. So how can the agent avoid collision? And in under this assumption, how can they reach the goal positions? And how can they do this in a relatively efficient manner? Right. And also what's important is what sort of capability do the agents have, right? Like what I said, the agent will have very limited capability, but do we allow them to sense the environment, or can we assume that they can somehow control their own speed instead of just following a constant speed? So these are important factors that really have a big impact on the performance of the solution. So this means that we're not facing a single problem, but we're facing a whole set of problems. And for each different instance of the problem, we can come up with a solution. I'm going to look at the very simplest case, which is the assumption when we have agents with no sensory capability, and the agent will only be able to follow uniform speed, which is, let's assume that's just 1 unit of time to travel through a single edge. So in this scenario, because the agent has no sensory capability, really what the agent can do is just follow some predetermined path. So if you think about a situation, for example, a car park where you have a number of cars traversing, suppose we implement a pathway so that, first of all, each lane is single direction, so you're not going to have two cars driving into each other, and so they're just following the same direction and in a uniform speed. And suppose that the pathways are designed in such a way that all the locations are traversed, then they will not collide into each other. So more formally, we can imagine that the space is designed in such a way that there is a Hamiltonian circuit of the underlying graph consisting of the nodes and the edges. So once we have a Hamiltonian circuit, remember a Hamiltonian circuit will be a path that visit every node once and only once, right? And then they come back to the same starting location, right? So once we have a Hamiltonian circuit, then what we do is for every agent, we just ask it to follow the direction of this Hamiltonian circuit and in the uniform speed. Then we can guarantee that every agent will be able to visit their target eventually because all the agents are visited, and also we can guarantee that there is no collision because everybody just follows the constant speed. So we can phrase this mathematically as a theorem. If the underlying graph G contains a Hamiltonian path, then traffic law 1 will guarantee that no collision occur and each agent will reach their goal in big O V steps, or V is the number of nodes. But there are a number of problems with this traffic law. Basically, if you think about it, although we're saying there's no central control, but the social law is so rigid in such a way that it essentially dictates the behavior of each agent. There's no room for individual planning and decision making. Right? And always rigid laws lead to suboptimal behaviors as a general principle in life. So as a result, we'll get very slow arrival time, and also high energy consumption if you think of these agents as just robots. And this is especially so when you have a very large state space. So it may not be really practical in real life. And you can see that the reason why we have such a traffic law is that the agents assume to have very, very limited ability. So if we relax some of the constraint in the agent's capability, then we can have some better protocol for the agents to follow. For example, suppose in this scenario where we have agents Q with no sensory capability, but then the agent will be able to change their speed. So traversing an edge UV may be a continuous movement from U and V within T time units rather than just fixing on one time unit. And they can change this T, right? So what is the best way to avoid traffic accidents? If you think about in a real life situation, the best way is to really slow down, right? If you want to avoid accidents, slow down, right? So what do? In the second traffic law that we're going to introduce, remember the agent are able to change their speed. Then what we do is we can order all the agents one by one. So we start from A1, A2 up to AM. The agent AI will start moving at time unit I, right? And each agent moves so slow that traversing each link takes exactly M time units, right? So for example, if we have 3 agents in the space, then we can let agent 0 starts at time 0, let agent 1 start at time 1, and let agent 2 start at time 2. And then to traverse each edge, the agent would take exactly 3 time units. Right, so you can see that they are quite slowly moving in the space. As an illustration, we can consider here we have 3 agents, and they are ordered as 1, 2, 3. Of course, you can think of it as 0, 1, 2. So if we implement such a social law, and if all the agents follow it, then we can ensure that the agent AI arrives at a node in V only at time unit I minus 1 modulo m, right? And because of this, you will never have two agents arriving at the same node at the same time, because the agents will arrive at this node in different times according to the modulo relation, right? The congruence modulo relation. And therefore we can conclude that the traffic law 2 will guarantee no collusion. Furthermore, for any goal that can be reached by an agent in isolation in t time unit, there exists a plan that reaches the goal in less or equal to t plus 1 times m time unit. So this means that essentially the agents can somehow follow their shortest path, but just with a constant blow up to the time that they would normally take if they act alone in the space. Right. So there's a bit of cost to the system, but you can see that if the number of nodes is very, very big, it does not really affect the efficiency of the agents, because the traversal time of the agent only rely on the length of the shortest path with a constant factor. Well, not really a constant factor, as a factor of m multiply on the time. So, but what if you have agents that are having more capability? For example, you could have agents that have sensory capability of close by nodes. Whenever they come up to another agent, they will be able to see the agent coming. And let's now assume that the agent will have uniform speed. Then in this situation, can we design a social law that is also good? Right? I'm going to give you a solution. In the solution, it's a little bit complex, more complex than the previous ones, as we need to somehow divide our physical space. We need to implement some sort of highways in the space, and then we need to design some giveaway rules. And also, not only the highways, we have local suburbs. We need to specify how the agent will act in these local suburbs. So this is really mimicking the sort of traffic laws that we have in our real life, right? When we drive. So imagine we have a situation where we have a very fixed underlying graph. This is just a graph, which is the grid. So it's an n by n grid. And then what we do is we will fix constant k and m, right? We will superimpose an m by m cursor grid on the original grid. So you can see that in the diagram, the bold lines indicates these cursor grid. Then for each of these bold paths, we implement a single direction rule on it. So some of the vertical lines are going from bottom to up, and some of the other ones are going from down up to down. So essentially they're following the zigzag law, which so you first of all go up, and then the next vertical line you go down and up and down and so on. Horizontally, you first go right and left and right and left and so on, right? So basically we implement these alternating up, down, left, right direction. And the agent, when it enters such a path, then essentially their behavior is dictated by these directions. So, and also we put a constraint that says the agent is allowed to change the direction at most k times every time it uses the highway, right? So if it changes k times, then it cannot use the highway. It has to go out of the highway. And the next part is we need to specify the giveaway rule. So when an agent enters a junction on the highway, they must wait for agent who also want to enter the junction but arrive there earlier. If two agents arrive there together, agents on rows must give way to agents on the columns, as illustrated by this simple example. And thirdly, we need to design the Suburban Rule. If you look at the diagram, you will be able to see that I zoom in a single suburb, and basically for every suburb we implement the same law. So in the suburb, you can see that it's surrounded by highways, but within it there are lots of small roads to follow, and typically the agent's target location will be one of the locations in this grid. So how can the agent step outside of the highway and then reach the goal location? Right. So we first of all require that the agent only enters an internal area from the entry point, which is at the left bottom corner of the suburb. Right. And then it can only move along the blue line horizontally to the right to reach to the location X in this grid. Right. If Y is unoccupied or someone is moving on Y, then the agent moves from X to G by moving only up and left. Right. So it can never touch the blue line. Otherwise, we just wait at X for one time unit. Right. And then the agent move along the blue line starting from G to the exit. Right. The exit is considered a junction on the highway, and from the exit it can then go on the highway. Right. And then we require that the agent cannot stop unless the agent in front does not move. So you can see that in this way, we are giving the agent's autonomy starting from the location X and ends at the location G, right? And if the agent has the destination, which is some location within this grid, from X to G, it can choose its own direction, and so it can choose its own path to get to the location that it wants to get to, as long as it only moves up and left, right? And once you get to that location, it can then follow on to get to the location G and then follow the blue line to the exit. So you can see that there's no autonomy from the entry to X. There's no autonomy from G to the exit, but there is some level of autonomy within the space, right? And after which it would just enter the highway and then potentially accomplish another task. So that's the traffic law that I introduced, and we can actually mathematically prove, although I'm not going to do it here, that the traffic law that I described guarantees no collision. And in fact, you can quite easily see it, because on the highway, because of the uniform directions that we implemented and the fact that the agent cannot change their speed, there's not going to be any collision. And whenever they enter a suburb, they also follow these rigid laws, and also they are quite limited in terms of the directions that they can go. There's not going to be any collision there. Right? And what about efficiency? We're going to also prove that in terms of efficiency, we did not lose much from the shortest path. So suppose that there are big O of square root of n agents, so there are not so many agents. If there are too many agents, then of course we're running into trouble. And suppose the m is equal to big O of square root of n, then for any goal that can be reached by an agent in isolation, in t time unit there exists a plan that reaches a goal in t plus 2n plus small o n time units. So that is our solution for the multi-agent pathfinding problem. You can see that there are some central issues that are brought up, namely the capability of the agents, and under these constraints, how would agents accomplish their task while not getting into trouble with other agents. So coordination is really the central issue here, and we achieve coordination through social laws. Next, I'm going to introduce another application, namely constraint satisfaction. Constraint satisfaction is a classical artificial intelligence problem, but usually in the first year, in the first AI course, we look at the single agent case. But in many scenarios, it's actually possible to allow multiple agents to solve the same constraint satisfaction problem. I'm going to introduce this problem to use first of all CSP, a mathematical problem defined on a set of objects, and each object can be in a number of states, but there are also a number of constraints that limit which combination of values that these objects can take. So normally we specify a set of variables, and each variable comes with their domain and a number of constraints. The solution of the constraint satisfaction is assignment of each variable to some value in their domain so that all the constraints are met. And now the question is to find a solution of a CSP if it exists, or indicate that there is no solution. A typical constraint satisfaction problem will be, for example, Sudoku, where the variables are the cells that we need to find a number for, and the domain of each cell will be a number from 1 to 9, but there are a number of constraints. For example, a number can only appear once in every row, in every column, and also in every 3 by 3 cell in the Sudoku grid. There are many other CSP problems, like the 4 queens problem, which we're going to discuss next. Formally speaking, we introduce the notion of constraint network. This will be a sort of a graph theoretical representation of a CSP, this problem. So we have a set of variables which are denoted by x, the x1 up to xn, and then we have a set of values. The domain will be a function that assigns with every variable xi some subset of d, right? So 2 to the d, that's really denoting the power set of d. So the domain function will be just a function which specifies the domain of any variable, right? And then we have the set const, which is a set of binary constraints on the set of variables, right? A binary constraint would be things that specifies how the combination of values of 2 variables are not legal, right? So, for example, in the 4 queens problem, that will be a problem where we have a 4x4 chessboard, and we have 4 queens, and we want to place the queens on the chessboard so that they do not create any conflict with each other, so that no queen will stand in the same row, in the same column, and also in the same diagonal. So you can imagine that here, abstractly, we have 4 queens, so each queen will be a variable, right? And we call them Q1, Q2, Q3, Q4, and each of the queen has domain. Well, they can have domain, which is a position in the entire chessboard, but just to be simple, because we cannot have 2 queens in the same row. So we assume that each queen will occupy their own row. So Q1 will be the queen in row 1, Q2 will be the queen in row 2, and so on. And as a result, each queen will only have 4 possible values, 1, 2, 3, 4, which is a column that they stand on. And then the constraint mathematically expressed can be saying Qi minus Qj, the absolute value of which cannot be the same as the absolute value of I minus j. So this indicates that any 2 queen will not be lying in the same diagonal. And also Qi cannot be the same as Qj for any different I and j, so they cannot stand in the same column. Right, so that would be a typical a description of a of a constraint satisfaction problem. We then continue on some more formal definitions for any subset of the variables, and instantiation will be a function which maps these variables to certain values in their domain. And instantiation is legal if it satisfies all the constraints that are defined on the problem. A solution will be a legal instantiation of all the variables. Right? So what we want from the CSP is to answer the question, does a solution exist? And if a solution exists, we want to find one. Right? The classical centralized method to solve CSP involve search methods such as backtracking and also other methods such as constraint propagation, local search, which has been extensively studied. So, but what we really want to find out will be how can we solve a CSP using a multi-agent system. And this means that we want to decentralize the problem. So we define a distributed CSP, which is basically treating a constraint network as a multi-agent system where each variable becomes now an autonomous entity. Right? So the variable being an autonomous entity, they're able to choose a value for themselves. But what we want to do is that they want to collectively meet the constraints. Right? And we also assume that the agent will have certain capability. For example, they are able to perceive the choice of course, themselves, and also those agents that are neighboring themselves. So in the graph, they look at their neighbors. These are the nodes who they have a direct edge linked to it. So they look at the decision of the neighbors. They're also able to, in a limited way, communicate with the adjacent agents, right? So this is our assumption, but we want to find a protocol such that if all the agents will follow the protocol, the multi-agent system eventually will decide whether a solution exists. And if it does exist, then by collective decision making over all of the agents and all of the variables, they will be able to find assignment of the variables in such a way that all the constraints are satisfied. I'm going to introduce one of the earliest solution to this problem, which is asynchronous backtracking. This was proposed by Japanese researcher Makoto Yuku in 1994. You can see that it's actually, despite the fact that this problem is so classical in computer science and the centralized version has been studied for decades, the multi-agent solution actually has not been around that long. It was started in the 1990s. Here the agents work asynchronously, and they assume to be able to exchange messages to collect information about the other agents. The key idea will be to use an ordering. So the agents are ordered by priorities. These priorities can be defined in an arbitrary way, but it has to be somehow linear, right? There will be a top priority agent and a second priority agent and so on. And the priority level direct the decision making of the agents, right? So if you think of a social hierarchy, the agent with the highest priority will make a decision and then pass the decision to the subordinates. And then the subordinates, also because they are in the hierarchy, that the next guy will make a decision and pass the decision on to the next guy and so on. But this social hierarchy would also need to implement a way for agents with lower priority to pass on message to agents with higher priority, right? So what we do is each agent will maintain a local state that contains their decisions and also their knowledge about others. An agent can request communication with also other agents. We next give a rather high-level description. If you really want to know the full description and the proof of the solution, you're encouraged to read the original paper by Yuku. But that's not the main purpose of this class. The main purpose is just to give you a snapshot of a multi-agent system and talk about the potential issues that can be brought up by such a scenario. So in this high-level description, we have agents who are ordered by the priorities. The edges are, so remember in a constraint network, the edges assumed to be undirected. But in this setting, because the agent has their priority, so in every edge, if you look at the two endpoints, there will be one agent who has a higher priority than the other one. So the edges are directed from higher priority agent to lower priority agent. And also a higher priority agent will be able to pass on their decision to the lower priority agent. And then, well, it's a fairly humane system in such a way that the higher priority agent would just not just pass on the decision, but also ask the lower priority agent whether the decision is okay. Right? So there's an okay message that's being sent. If it is okay, then the lower priority agent will execute this decision. And if it's not okay, then the lower priority agent will just send back a no good message saying that, this decision is no good for me and you have to change. Right, so that's the general social system that we try to implement. Let's look at this case study, which is the 4 quints problem that I introduced. We have this 4x4 board, and then in each row we have a quint. So in this case, it would just be an agent. And remember, the constraint is that they cannot stand on the same column. They cannot stand on the same diagonal. Right? Either direction of the diagonal are not allowed. So we can define an initial configuration where all the agents are placed at the first column. Of course, this is not a legal solution, and they have to somehow adjust their own positions. But according to our solution, the agent need to have a priority. And let's assume that the priority is defined by the row, so the top agent at row A will have the highest priority. And because it has higher priority, it would just say, okay, now I wait and I pass on my decision to all the people who are below me. That's B, C, and D. He passed on these decisions saying that, okay, I'm not at location 1. Is it okay with you? Right? So now the lower priority agent will try to satisfy the higher priority agent as much as possible. So at the second row, the agent B will say, well, because the first agent is staying at position 1, in order to not create a conflict with him, I need to move to location 3, because 1 and 2 both create a conflict. So the second agent will decide to move to location 3. But before he does that, if you look at the third agent, C, at this third row, he sees that the first agent is at location 1, and the second agent is also at location 1. So the third guy will say, okay, in order to not create a conflict with both of them, I need to move to location 4. Right? And now if you look at the last person at the fourth row, so after observing the current decision, the initial decision of all of these agents, you can see that there's no location that's good for her. Right? So she needs to report a no good message to those above her. Right? And because there are 3 agents who have higher priority than this agent, who does the agent report to? Right? We assume that the no good message only pass 1 level up to the person with the lowest priority that's above this agent. So the no good will be passed on to C. Right? So at this step, at the next step, you can see that according to our reasoning, agent B moves to 3, agent C moves to 4, and agent D moves to column 2. And of course, the agents, after they executed this decision, they will need to pass on this message to lower priority agent saying, is it okay if I do that? For example, agent B would send a message to agent C saying, is it okay, I'm at position 3? And agent C will send a message to agent D saying, is it okay if I move to position 4? Once this is received, once all these messages are received by agent D will find the location 2, which is not creating a conflict with either of these agents, right? But when agent C receives the message from agent B, he can see that this is no good because there's a conflict created with agent B, so that it needs to report a no good to agent B, asking him to change. Right. And so when this happens, agent B will say, well, then I have to move again to position 4. But once the agent moves to position 4, he would then send an OK message to also agent C and D, and in particular agent D will see that, okay, now there's a conflict between my position and B's position, and because I have lower priority, I need to find another location if possible. And also at the same time, agent C also need to do the same, and agent C has a higher priority, so agent C will occupy the location 2. But also after he occupies location 2, he sends this message, OK message to agent D. And now agent D will see that, okay, it's not good for me to be in position 1, not 2, not 4, and also not 3, because that will create a conflict with 2. So agent D really has no place to go. And at this point, agent D needs to send a no good message to C saying that, well, I have nowhere to go, you have to change. But in this sense, agent C also has nowhere to go. You need to pass on the no good message to agent B, and agent B also has nowhere to go. So you need to pass on this message to agent A. So agent A has been waiting for all this time because it has the highest priority. It can just wait for people below him to make a decision. But now finally he receives a no good message from agent B. He knows that it's not possible here for him to stay at this location. He needs to go to the next location. Namely 2, right? And then after this, he sends all of these OK message to all the people, and then they restart this decision-making process until they eventually find a solution. And if you continue on this reasoning, you can see that eventually they'll reach a consensus where they will find a solution that doesn't just jeopardize any constraint. So here I'm giving you the entire picture of the decision making of a single agent. It consists of several modules. In particular, it consists of a module of waiting. It's waiting for message to arrive. It could be either an OK message from people who are above the agent, or no good message from those agents who are below the agent. And once you receive either of these type of messages, you need to act correspondingly. And there are some other modules that the agent need to implement. For example, try to choose a value. So here, when the agent is trying to choose a value, it may be that it's possible to find the value, and in this case, the agent will just change the value. Also, it may be possible that it is impossible to find the value. So in this case, some no good message need to be sent out. So if you examine this picture, you can see that although it looks quite complicated, it's really implementing in a natural way the procedure that I described earlier in that example. I'm not going to elaborate too much of the data structures of the agents and the exact procedure that they need to execute. You can examine my pseudocode that I put on the slides. So in summary, I hope that this lecture has given you a rough picture of multi-agent system and how it can be applied in different scenarios. In particular, we have looked at 2 problems. One is the pathfinding problem, where the goal is for the agent to reach their location without creating collision with each other. There we use social laws to enforce the desirable outcomes. But we need to take into multiple factors that includes whether the agent have perceptions or the agent have the ability to change their speed. We then move on to discuss constraint satisfaction problem, which is a classical single agent AI problem, but we turned it into a distributed constraint satisfaction problem to be solved by multiple agents. So here the agents are participating in solving the same problem, but still they need to coordinate with each other so that they can satisfy all the constraints that are described. One important mechanism that we introduced is the ABT algorithm, where the agents are arranging these priorities. And then they pass messages like OK message and no good message between each other, essentially carrying out a sort of search, but it is a search in a decentralized manner. Right. So that finishes this lecture, and I'll see you in the next lecture.